Alright, well, if you watched the last video for section 2.3, we did long division, and I showed you how to I did some examples of long division, and then I talked about another type of division called synthetic, where your divisor is in the form x minus c, and as you can see, the last example that we did on the previous video is the first example that I'm going to do here. So I'm going to show you how to do the same problem by using synthetic division. Now, synthetic division, what you're going to do is you're going to take, and first off, descending order, every term complete, descending order, every term there. If you have placeholders, put the placeholders in. But in this case, I have x squared, I have x to the first, I have x, the constant, or x to the 0. So I take the coefficients in the constant term here, and I take the 3, the negative 14 because of the minus, and the positive 15 because of the plus. I leave a space here, and then I draw a line. It's like a total line because I'm going to be adding. And then I am dividing. It has to be in the form x minus c, and this is indeed x minus c. C in this problem is 3. So you're going to put the value for c, I'm going to put a little pocket there, I'm going to put that value for c right here. That's my divisor, that's my dividend. Now, it looks a little weird because there's no answer, in sight, but I'm going to get to that point in just a moment. But once it's set up this way, here's how you go about the use of synthetic division. The first number in the dividend, the first coefficient, the leading coefficient, there's nothing underneath it right now, you just bring it straight down below the total line. It's like a 0 there. Then you take the c value, which is 3, and whatever this is, you multiply it times this number down below. So in this case, it's 3 times 3, 9. The 9 stacks underneath the next term in my column, or in my row here. So now I'm going to, I said this is a total line, I'm going to add these two numbers together. So a negative 14 and a positive 9 is a negative 5. And I repeat this process, because now I'm going to multiply the 3 times the number I just brought down. 3 times negative 5 is negative 15, I'm going to put a negative 15 here. And then I'm going to add down, because again this is a total line, and it's a 0. Now I normally, you don't have to, but I normally circle that last sum in the last column, because this guy right here is my remainder. You may, if you watched the last video anyway, you may remember that I did have a remainder of 0. That x minus 3 is a factor of 3x squared minus 14x plus 15. But where is my answer? Right here is my answer. These are the coefficients in constant terms of my answer, of my quotient. I work backward. I start with the first one here, ignoring the remainder. I know that that's my constant term. So this is my x to the first term, and if I had more, x to the second, x to the third, x to the fourth, what have you. So this is my constant term, and this is my x term. So it's 3x, and my constant term's a negative 5, so I write minus 5, and there is my quotient. The same quotient that I got, that I was able to determine when I was working the last video and using long division. But a lot less work and a lot more concise, more efficient. But again, the disadvantage to synthetic division, it has to be in the form x minus c. So let's try another one here. 4x to the third minus 28x minus 7x minus 3. These are in descending order, but I'm missing the x squared term. There's no x squared term. So before I put a plus 0x squared, well, I'm going to do that. I'm going to write the 4, and then since there's no x squared term, I'm going to put a 0 for its coefficient, then the negative 28, and then the constant term, the negative 7. And leave a little space, draw my total line, put my pocket there. X minus c, same exact divisor, so it's 3 again. Bring the first number down because there's nothing there to add to it, so that's a 4. Then we multiply, which is a 12. 3 times 4 is 12, stack it underneath. Then we add, that's 12. Then we multiply, 3 times 12 is 36. Stack it underneath the next one. Then we add, positive 8. Then we multiply, 3 times 8 is 24. Then we add, 17. And again, I'm going to circle this one. It's in the last column. That's my remainder. My variable is x. This is my constant term, my x to the first term, my x to the second term. So I have, let's see, let's put it right here. I have 4x to the second plus 12x, positive 8, plus 8. Now, how do I write my remainder? I write my remainder the same way as I did before. I have a positive 17 here, so plus 17 all over my divisor, x minus 3. I kind of squeezed it in there, but there's my answer. Now, if you do this in a more traditional manner, you're going to use all of this space, not just this. This is much more efficient. One more here that I have, and then we'll talk about the remainder theorem that uses synthetic division. This guy here divided by this guy here. This guy here is not in descending order, and it looks like it's missing a term. I have an x to the fourth, I have an x to the third, I don't have an x to the second, I have an x and I have a constant. So I'm going to be very careful here. I'm going to put the x to the fourth here first, that's the 2. The x to the third plus 7, that's the 7, positive 7. I do not have an x squared term, so a 0 for 0x squared, a negative 3 for the x term, and then my constant term is a positive 5. Leave a space, total bar, pocket. Now in this case, it's a plus 1. Think of x plus 1 as x minus a number, so it would be minus a negative 1. So C is negative 1, and that's what goes in the pocket. Lots of mistakes here, people putting down the wrong sign. It's kind of the opposite of what it looks like. It looks like a positive 1, negative 1. It looks like a negative 3, positive 3, if that helps. First one comes straight down, then I multiply, that would be negative 2, then I add 5. Then I multiply, negative 5, then I add negative 5. Then I multiply, positive 5. Then I add positive 2. Then I multiply, negative 2. Then I add positive 3. Circle that. That's my remainder. I can already tell you right now, because my remainder is not 0 like it was in this example, x plus 1 is not a factor of that polynomial. So that's kind of a neat thing. So now, what's my answer? Well, this is my constant. My x to the first, my x to the second, my x to the third. 2x to the third plus 5x to the second minus 5x plus 2 with a remainder of 3, positive 3, so plus 3 all over x plus 1. And this would be my answer. Now if you're saying, well, is it always a plus? Well, if this number, if this remainder is positive, yes. If it's a negative, I usually put the minus sign there and then write it down. If this had been a negative 3, I would have had a minus sign there. Now, I kind of wrote that poorly. Maybe because I thought I was going to run out of space, but I'm going to rewrite this a little bit because I don't want you to think that the plus sign somehow is connected to just the denominator of this. And that looks a little bit better. There we go. Now, we can use synthetic division for a number of applications. And the first one that we're going to look at is what we call the remainder theorem. The remainder theorem says if a polynomial f of x is divided by x minus c, notice that form so I can use synthetic division, then the remainder is f of c. This is kind of cool. This says if I plug whatever this number is into here and figure out what that is, evaluate f of c, that's the remainder of my division. So that's one way we can find the remainder. If the problem says here's a polynomial, here's what you're dividing by, and it's in the form x minus c, find the remainder. I can just plug it right in. Now it depends on the polynomial. I mean, that's a fairly simple polynomial. Plugging 3 into here would be pretty easy. But if I had a much more complicated polynomial and I was plugging in a negative number or a fraction or something weird, a radical, then it can kind of bog you down. But we can also use synthetic division because we know that the remainder is right here. It's in the last column. So when we do synthetic division, to find this value, to find, quote, f of c, we don't really call it synthetic division anymore. We call it synthetic substitution to find it. Okay, and key, and I mentioned it here, if f of c is equal to 0, that means x minus c is a factor of f of x. If it divides into it evenly with 0 remainder. Now, given this guy right here, use the remainder theorem to evaluate f of 5. Well, f of 5 is the remainder if we take this f of x and we divide by x minus 5. Because that's my c value. So I can use synthetic substitution here to find f of 5. Well, do you want to plug 5 in? You can. 5 to the 4th is 625 plus 125 minus, what is that going to be? 150 minus 25 minus 15. Not impossible. Get Mr. Calculator out to help you there. Or I can do this with 1, 1, negative 6, negative 5, negative 15, 5. So that's a 1. That's 5. That's 6. That's 30. That's 24. That's 120. That's 115. That's 575. That's 560. There we are. I have the same thing. Now go ahead and go plug it back in. You know, plug it into here. 5 to the 4th. 625 plus 5 to the 3rd. 125. That's 750. Minus 150. So that'd be 600. Minus 25. So that'd be 575 minus 15, 560. If your arithmetic skills are fine and you don't want to, use this, that's fine. But this makes it a little bit more efficient. Right over to here, f of negative 3. I can find f of negative 3 in the same manner. Now this time you'd have to plug in a negative number. It makes it a little bit more confusing. Or at least you have to be a little more careful with your signs. I'm going to approach it the same way. Negative 3 is my c value. It's like I'm taking this polynomial and dividing by x plus 3. So a negative 3 goes right in here. And I'm looking for this guy, whatever that might be. So 1, negative 3, add negative 2, multiply 6, add 0, multiply 0, add negative 5, multiply positive 15, add 0. So not only do I know that f of negative 3 is 0, I know that x plus 3 is a factor of f of x, because my remainder was 0. Very nice. This one here. Use the, I'm going to kind of clear a little space out over here, because I wanted to actually do one more example that's connected with this problem, but I didn't have space really over there. Use the remainder theorem to determine if the given number c is a 0 of the function. Now let's think about what a 0 is. The 0 means that when you plug it into the function, in for x, in for the independent variable, it equals 0. So if I plug 2 into this, and it equals 0, there's my guy. Well, all I'm doing is the same thing here. I'm just looking for 0 here. That tells me back here, negative 3 is a 0 of that function. Perfect. So I'm going to use synthetic substitution. Be careful, there's no x cubed term there. So I have 2, 0, I don't know if you can see this very well, negative 3, 5, negative 11. And I'm interested in right here. I'm interested in this is a 0. If this is a 0, my answer is yes. If this is anything other than 0, my answer is no. So let's plug in 2. So the 2 comes down, straight down. 4, then we add, then we multiply, then we add, then we multiply, then we add, then we multiply, then we add. Nope. As you can see, it doesn't equal 0. Let's try this guy right here. 2, 5, negative 14, negative 35. Now I have to be a little bit more careful here because I'm not dividing by an integer. C is the square root of 7. This will be fun. First number comes straight down. Then we multiply. That's 2 times the square root of 7. Then we add. Be careful now. This is 2 square roots of 7 plus 5. Don't get your calculator out and approximate it. Then we multiply. 2 square roots of 7 times this. Well, 2 square roots of 7 times 2 times the square root of 7 is 14 plus 5 square roots of 7. So this is 14 plus 5 square roots of 7. Then we add the negative 14, the positive 14, 0. So I have 5 square roots of 7. Then we multiply. Square root of 7 times 5 square root of 7. Square root of 7 times square root of 7 is 7. So that's 35. Look at this. I have a remainder of 0. So yes, the square root of 7 is indeed a 0 of this function. Now, I'm going to do one more here with this function right here. Here's my part C. I have f of x is equal to x to the third minus 7x to the second plus 16x minus 10, and this time I'm going to let c be an imaginary number, 3 plus I. Here we go. 1, negative 7, 16, negative 10. After you do a few of these, it becomes fairly easy process. But at first, practice these problems. Make sure you understand each step so it becomes a little bit more automatic. So 3 plus I comes right in here. Here we go. The 1 comes down. 1 times 3 plus I is 3 plus I. Negative 7 added to 3 plus I is negative 4 plus I. Then we multiply. Ooh, this is going to be a mess. I have 3 plus I times negative 4 plus I. A little scratch work here. So this is negative 12 plus 3I minus 4I minus I squared, or plus I squared is negative 1. So I have negative 13 minus I. That goes right here. Negative 13 minus I. Yikes. Then we add 3 minus I. Then we multiply. Well, this is nice. These are conjugates. So when I do the arithmetic here, I have 3 plus I times 3 minus I. That's going to be 9 minus I squared, which is going to be 9 minus a negative 1, which is 10. So that's a 10 here. Look at that. Remainder of 0. That means this function does have a 0 of 3 plus I. So this is really good at helping you to either validate or even determine the zeros of a function using synthetic substitution and the remainder theorem.